Hi everyone. So in this video, I want to give you all an introduction to what we call free body diagrams. And you can see the outline here on the left. So the first one is just drawing free body diagrams and then talking a little bit about normal forces, which is something that you'll hear a lot when you're um, drawing free body diagrams and working with forces. And then last, how you use a free body diagram to help you actually solve problems. And usually the way that works is you use Newton's second law, having your free body diagram for reference as sort of the basis of what you're doing. So let me talk through all these things. So all a free body diagram is a picture that shows you all of the forces acting on an object. So for example, if I had a situation in which I was pushing a box along the floor, I could draw that. So let's say here's a floor. Here's a floor. Here's a box. And here I am. I guess it's a pretty big box, the way I'm drawing it. Here I am pushing a box along the floor. There's going to be forces acting in this situation. And it will be helpful to know what those are, because if I know what the forces are, then I might be able to figure out something about the acceleration of the box, which is ultimately what I have. So the question that I'm trying to answer here, the motivation for all of this is, what is the acceleration of the box? So the way that I go about this is I try to think of and then draw all of the forces acting on the box. So usually when you have a problem like this, and there's multiple things in the system, so there's really three things in this system right now. One thing is, I'll call thing one the box. Thing one is the box. Thing two is me. And three is the floor. And when we draw free body diagrams, I could try to draw all of the forces acting on everything here. So the forces acting on the box, me, and the floor. But oftentimes, you don't have to do that. It's usually easier, or often easier, to break the problem down into parts and then figure out the forces on each individual part. So if I want the acceleration of the box, really all I need are the forces on the box. If I know the forces on the box, then I can find the acceleration of the box. So I'm just going to concern myself with the box. And the way that I'm going to do this is I'm going to draw a free body diagram for the box, which is kind of important. So when I'm doing this, I want to emphasize for the box, because that means that I'm only considering forces that act on the box and no forces that don't act on the box. So if there's a force on me, I'm not considering that when I'm drawing the forces on the box. And maybe this will make sense as I start to talk about it. So let me draw the box by itself. So here's the box. Box. All right. So what sort of forces act on this box? Well, I've said that I'm pushing the box. So I'm pushing the box. That's a force that I'm applying on the box. So the force that is I'm probably pushing it to the right, let's say. So that's the F of the push. I'll call it F sub push. So that's what I'm doing. What other forces are acting on the box? Well, if this problem's happening on Earth, and let's assume that it is, then there's some gravitational force from the Earth. So the Earth is pulling down the box. So that is a force that acts downwards. So I'll represent it on the box this way. I'm not really going to be concerned with the length of the arrows that I'm drawing here to represent the forces. We'll figure that out afterwards. You can consider the length of the arrows to tell you something about the relative size of the forces, but we don't necessarily know. We haven't been given enough information in this problem really to know that at this point, so I'm not going to be super concerned with that. Although we know for sure that if the box is getting pulled down by gravity, there has to be something holding it up. Like, why isn't the box just falling towards the center of the Earth? Well, there has to be some force up from the floor. And I'm going to call this force N, and that's going to mean normal force. So, and I'm going to talk about what a normal force is here. So this is normal force. But really all it means in this context is the force um, from the floor that holds up the box. That's really all it means, and I'll expand on why it's called a normal force here and what that means. And we can make this model more complicated. I mean, maybe this model is sufficient, but usually there's friction. So there's probably friction between the box and the floor. And if I'm pushing the box to the right, then it probably makes sense to indicate friction pushing against that motion, because friction will tend to slow things down or decelerate things if they're moving relative to each other. So that means that there's probably some frictional force here that points this way. I'll write it like this, for a fancy F for friction. And that's a pretty good model. We could add other things in here too, like we could add in air resistance, or we could add in other weird forces that we could think of, but that's a pretty good model for what's happening to the box. And this is more or less a complete free body diagram for that model. We could choose, like I said, we could choose to add other forces to this, and we could do that. That would change the model that we're using to solve this problem. And the model that we have here is pretty good, probably. Okay, so that's what a free body diagram is. Anytime you have a problem where you're trying to find the acceleration of something or the force applied to something, usually a free body diagram is where you start. So the reason for that is because this is a way to get a sense of what's happening in the problem, to just have something where you've drawn everything that's actually affecting the motion of the things that you're concerned about. And it's a really good basis for launching into actual quantitative problem solving. And I'll show you that when we get to the third part of this video, when we talk about Newton's second law. But let me pause for a moment to talk about normal forces. So a normal force is just a contact force. So normal forces are contact forces. And what is a contact force? A contact force is just a force that happens when two things are in contact with each other. So what does that mean? So for example, in the box case above, the normal force there is the force from the floor on the box. And that only happens because the box and the floor are in contact with each other. The force can't exert a force on the box, the floor can't exert a force on the box unless the box is touching the floor. If I put my hand into the wall and push on the wall, I'm exerting a contact force on the wall, and the wall's exerting a contact force on me. We can't exert force on each other. I can't exert a force on the wall without touching it, without being in contact with it. And that's what normal forces are. They're forces of contact. Why they're called normal forces. So why is this called normal force? Normal is another word for perpendicular. So in math, if you say normal, it means perpendicular to. So if you think about how contact forces work, perpendicular. So if I think about how contact forces would work, we can consider a couple of situations. So in the situation above, if I have my box sitting on the floor, then the force that the floor exerts on the box points up. So you'll notice that if I imagine sort of extending these lines, the force points perpendicularly to the surface that the box is in contact with. If I imagine tilting the floor, maybe I have a ramp or something like that, and then putting a box on the ramp, then the force that the ramp exerts on the box will also be tilted. It's just going to push the box out from the ramp. It can't push it straight up. It can't push it sideways. It does those things a little bit, but really we're representing that with some force that points perpendicularly to the ramp. So again, the force there, and these are normal forces. These are our contact forces. So let me indicate that. So these normal forces here are always perpendicular to the surface that is between these two objects that are in contact. And I could draw more exotic examples, but the result would always be the same. So the contact force between two things is always perpendicular to their surfaces in contact with each other. And we'll keep looking at more examples of that as we go. But that's why it's called normal force. So these contact forces, which are perpendicular to the surfaces, normal is another word for perpendicular, so we call those normal forces. So really, when you hear normal force, just think this is a force that describes the force of two things just touching each other. That's all a normal force is. So lots of things can qualify as normal forces. So my example of me pushing into the wall, I'm exerting a normal force on the wall, and the wall is exerting a normal force on me. You could think of it that way. The box example, the box is being pushed by the floor, so the floor is exerting a normal force on the box, and also the box is exerting a normal force on the floor, and so on. And pretty much any sort of contact force like that, two things pushing against each other, you could call it normal force if you want to. You'll see that kind of force show up in lots of these problems. Okay, so let's go back to our box example for a second. I'm going to redraw it down here. So using FBDs with Newton's second law. So Newton's second law is F equals ma. So, or more precisely, the net force is equal to mass times acceleration. And it's really important that that's net force. You have to consider all of the forces acting on an object before you can know something about how it's going to accelerate. So to redraw the free body diagram from our box above. So here's our box. We said there's a pushing force. We said there's gravity force. We said there's a normal force. And we said there's a frictional force. I'll just indicate that fancy F sub FR. Okay, so how do we actually use this to solve problems? Well, we establish a coordinate system. So here, what we want to do is we have a picture of all forces. So this is going to tell us something about the net force. The free body diagram tells us something about the net force. And that's useful because if we want to find acceleration, we need to know something about the net force. So what we can do is, if we establish a coordinate system, so let me establish that this way is positive x, and this way is positive y. Forces are vectors. Acceleration is a vector. And so just like a vector, I can break down forces into coordinates. So when I'm writing net force equals ma, I'm really writing two things if it's a two-dimensional problem. What I'm really writing is I'm writing the net force in the x direction is equal to mass times the acceleration in the x direction. And I'm also writing that the net force in the y direction is equal to the mass times acceleration in the y direction. So if I had a third dimension in this problem, which I don't, I could write a third equation. And in general, when I write F net equals ma, that's three equations for the three spatial dimensions that I have. Okay, so really what I'm doing here is I'm trying to add up all of the forces in the x direction. That's what the net force in the x direction means. And add up all of the forces in the y direction. That's what the net force in the y direction means. So let me do that. So in this case, the way I would use my free body diagram is to say that, okay, in the x direction, if I'm looking for the net force there, I have two forces that point in the x direction. One is my F push, and that points in the positive x direction. So I'll write that I've got F push. And then in the negative x direction, I have the frictional force. So I'll subtract the frictional force from the push force, and that gets me the net force in the x direction. That's then going to be equal to the mass times the acceleration in the x direction. Excuse me. And I can do the same thing for the y direction. So in the y direction, in the positive y direction, I have the normal force. In the negative y direction, I have the gravitational force. So I add them up that way, and then that's equal to the mass times the acceleration in the y direction. I haven't given any numbers to these forces right now, so we can't really go any further than that at this point. If I said that the push force was 100 newtons and the frictional force was 30 newtons, then we could start solving for stuff here. But there is one more step that we can take. In a problem like this, sometimes without any numbers, you can still do some stuff. And one thing you know already is if I'm pushing this box along the floor and the floor is flat, then the box is not falling into the floor and it's also not accelerating up off the floor. Particularly if I'm only pushing it horizontally, there's nothing that would make it sort of go up or down. So that means that the acceleration in the y direction has to be 0 in this case. So this is true. True because of the physics of this case. Because of physics, of physical reasoning, I'll say. That wasn't given in the problem. We just could figure that out from the statement of the problem. And if that's true, then we can know something else. So this says that this y equation is telling us that the normal force minus the gravitational force is equal to 0. So in other words, the normal force here is equal to the force of gravity. This is true now no matter what the force of gravity on the box is. And that's kind of a cool finding. In several problems, this will be a result that is true, but it's not always true. This is not always true. This is only true because of the acceleration being 0, because a sub y equals 0. There will be lots of cases where normal forces aren't equal to the weight. So for example, the example I gave of me pushing into a wall, if I'm pushing into the wall, I guess probably how hard I can push into the wall has something to do with my weight, but I could push the wall lightly, I could push the wall hard, I could push the wall after being smashed into the wall by a rhino, and so there's lots of values of the force that I can push into the wall with that aren't my weight. So there's nothing fundamental about normal force being equal to gravity. It just turns out to be that way in this case. So that's a way we can start to use free body diagrams to analyze physics problems. And it's a really powerful technique, and we'll see how powerful it is as we go along. But this is a quick introduction to free body diagrams and using them to solve problems. I hope it was helpful, and I'll talk to you guys soon. Bye.